All right, let's jump right in. We're about to go on a journey deep into the quantum world to solve a puzzle that has stumped physicists for years. It's a mystery about speeds that seem, well, frankly, impossible. So it all kicks off with this really weird question. What is the speed limit for forgetting? I know, it sounds a little philosophical, right? But in the world of quantum mechanics, this is a very real and incredibly important puzzle. It's all about how quickly a group of tiny particles can lose their collective memory, their perfectly synchronized dance. And the timescale we're talking about here is just 1 femtosecond. Now, to get your head around that, a femtosecond is 1/quadrillionth of a second. Let me put it this way. 1 femtosecond is to 1 second what a single second is to about 32 million years. It is a just mind-bogglingly fast slice of time. Okay, so this whole forgetting thing actually has a technical name. It's called dephasing. The best way to picture it is to imagine a room packed with thousands of clocks, all ticking away in perfect, beautiful sync. Dephasing is what happens when, one by one, they start to drift, losing that shared rhythm until the whole room is just this chaotic mess of noise. That's exactly what's happening to electrons and certain materials. And this is where our mystery really starts. For years, scientists have been watching this dephasing process. And in some of our most advanced materials, it's happening way, way faster than any of our scientific theories can possibly explain. It's a genuine scientific whodunit. The crime scene, if you will, is inside these super advanced materials like graphene, that incredible one-atom-thick sheet of carbon, and another two-dimensional material, molybdenum disulfide. Inside these things are quantum clocks. The electrons are just falling out of sync at this completely baffling rate. And the usual suspects, things like electrons just bumping into each other, they're just not fast enough to explain it. Something else has to be going on. And this slide really shows you just how big the problem is. Our best physical models, everything we thought we knew, predict this dephasing should take around 300 femtoseconds. But what do the actual experiments show? About 4 femtoseconds. That is nearly 100 times faster. This isn't just some small rounding error. It's a huge, gaping hole in our understanding of the quantum world. So to crack this case, recent research has pointed to 2 key players, 2 hidden processes that involve light. These are our main suspects. Let's meet them. So here they are, our 2 suspects, side by side. Now, don't get bogged down in the technical stuff. Just look at the shapes. On the left, you've got broadband emission. It looks like a messy, broad hill of energy, kind of like random static. But on the right, Dick superradiance. See how it's a sharp, powerful peak? That's our orderly quantum choir. These 2 completely different signatures are right at the heart of this whole puzzle. All right, first up is broadband emission. The easiest way to think of this is just background noise. When electrons get all energized or hot, they scatter around and spit out light in a totally random, messy way. It's a lot like the thermal glow from a hot piece of metal, just a chaotic jumble of energy. But Dicke's superradiance? Now that is something else entirely. Imagine a huge choir, but instead of everyone singing whenever they feel like it, they all hit the exact same note at the exact same instant. The sound would be incredibly powerful, right? That's superradiance. Atoms are emitting light in perfect collective unison. It creates this short, intense burst that's way, way stronger than just adding up the individual parts. Okay, so we've got our suspects, the chaotic noise and the perfect choir. And here's the big twist, the key insight from the research. It turns out they don't just happen at the same time. They actually interfere with each other, and they do it in a really destructive way. And here you have it. The aha moment, straight from the paper itself. The researchers found a strong, destructive interference between these 2 light-emitting processes. This is the crucial clue. It's not one or the other causing this crazy speed. It's how they interact that changes absolutely everything. So how does that even work? Let's break it down. Step 1. The random scattered electrons create that messy broadband light. At the exact same time, the atoms collectively unleash their powerful, coherent flash of superradiance. And then, this is the key part, these 2 forms of light collide. Think of 2 waves in a pond meeting each other. If the peak of one wave hits the trough of the other, they just flatten out. That is exactly what's happening here. They're out of phase, so they almost perfectly cancel each other out. And that cancellation, that's what solves our speed puzzle. But wait, how does canceling out light explain an impossible speed? Good question.
This is where the evidence comes in, and it's what finally cracks the case wide open.
So here's the crucial bit. This destructive interference creates something that paper calls a scaled-down effect. It's kind of like a quantum magic trick. The real physical process, the actual electron scattering, is still happening at its normal, slower speed, a few hundred femtoseconds. But the interference acts like a fast-forward button on what we can see, making the dephasing look like it's all over in just a few femtoseconds. Okay, I know this graph looks a little complicated, but the story it's telling is actually super simple. Along the bottom, that's how hard we're hitting the material with a laser. The vertical axis is the signal we measure. See the circles? That's the real-world data we couldn't explain before. And the squares? Those are the predictions from the new theory, the one with the two kinds of light interfering. Just look at how perfectly the squares line up with the circles. This is it. This is the proof the theory perfectly matches reality, and it finally closes that huge gap we saw earlier. And if you need a smoking gun, here it is. The theory says that the closer the atoms are, the stronger that choir effect should get. So on this graph, moving to the right along the bottom means the atoms are getting closer and closer. Now look what happens to the signal strength on the vertical axis. It doesn't just go up, it skyrockets. This is exactly what the theory predicted. It proves our quantum choir is real, and it's the engine driving this whole mystery. All right, so case closed. But why should we care? Why does solving this tiny femtosecond scale puzzle actually matter in the real world? Well, it turns out this discovery opens up some pretty incredible new doors for technology. Yeah, this is so much more than just an academic curiosity. Solving this puzzle gives us a totally new way to understand and maybe even control electrons. It's a huge milestone for developing things like quantum computers that are less prone to errors. It could even unlock a whole new class of electronics that operate at petahertz speeds. That's thousands of times faster than anything we have today. And that brings us to a final, really fascinating thought. This whole effect is based on destructive interference. But what if we could learn to control it, to tune it, or even flip it? Could we one day design materials that use this quantum trick to process information at the absolute speed limit of the universe, the speed of light itself? The case of the femtosecond code might be closed, but the story of what we can do with this knowledge, well, that's just getting started.